Okay, so let us start because it's 3. So, can you see the screen? Okay. So, let us start. So, this week we are still discussing with this basic notion of vector space. So, that is our Hilbert space, and how to write operators in matrix representation and all that thing. So, how to take inner products, how to find trace, how to find expectation value in this new Dirac bracket formalism. So earlier we had done them in wave function method, so by doing position space integral. So now we will be doing vector space algebra. So the first question, so this is from the assignments. So you are given two states. One is this psi and another one is this chi. So both states are linear combination of some phi1 and phi2 kate. So these are these two basis kates, and they are said to be forming an orthonormal and complete basis. So phi1 and phi2 form a complete orthonormal basis. So phi1 and phi2 form a complete orthonormal basis, and we have expressed two states psi and chi as their linear combinations. So we have to find this trace of this outer product. So this is called an outer product. So if we write a kate first and then bra like this one, so bra in the right hand side of a kate, so that denotes an outer product. So okay, so I need to ask you, so are you familiar with how to take these outer products? Like they are also called the Kronecker products. So in this problem, this is not necessary to take the outer product, but in general, so do you know? Okay, so since it is not entirely necessary for this problem, so let us proceed. So we need to find the trace of this thing. So another thing, the inner product is a scalar, right? So this is like inner product is like dot product of two vectors. But what about outer product? So what is it? So is it a scalar, like is it a number, or is it a state, or is it an operator? So operator means, so is it a matrix? So what is this outer product thing? So unlike the inner product, so outer product is a matrix. So this is the outer product or Kronecker product of two vectors. So psi is, so usually we denote by psi a column vector, like a kate denotes a column vector and a bra denotes a row vector. So this is outer product between a column vector psi and row vector chi. And then we take the inner product and get a square matrix. So this outer product is actually a square matrix, and we need to find the trace of that square matrix. Of course, the explicit representation of that matrix will depend on the basis we are using. So that is always there. But in this basis, so these representations, like the linear combination representation, so these are basis independent representation. So when you will write the explicit row vector, column vector form for psi and chi, then the importance of basis will come into play. Otherwise, this is just, so as is given in the question, so this is just a basis independent expression. So of course, if chi is given like that, if chi is given like that linear combination, then the corresponding dual state or Bra state will be given like this. So please note that this minus I has to be complex conjugated here, and that gives I by root 2. And then corresponding to phi 1 and phi 2 kets, the corresponding bras are written. So chi, so the dual vector of this chi ket state is written like this. And we do not need to find the thing for psi. So psi is already given as a ket state. So now consider this. So as I said, this outer product means it is actually a matrix, or more generally it is an operator. Like it is, it is absolutely not a number. So let us denote this outer product as this. So M is, you can think M as a matrix. So we need to find the trace of that matrix. And since psi 1 and psi 2 form a complete and orthonormal basis, so you are not familiar with outer product. Okay. Anyway, so in this problem, so since psi 1 and psi 2 form a complete and orthonormal basis, and you know the formula for trace in such a basis, right? So this is the trace formula. So how to find trace? So this is the trace formula, like you take the expectation values with respect to the basis states that form the complete and orthonormal basis, and then add them up. And the denominator things are for normalization. So the kets with respect to which you are taking these expectation values has to be normalized. So in essence, trace M means, so this is the expectation value of this M operator in phi 1 state, and similarly this is the expectation value of M operator in the phi 2 state. So it's nothing, just the expectation values, and if you add this, if you add all these expectation values, you will get the trace. So here we are considering this two-dimensional Hilbert space, so that is why only two contributions will be there, like one with respect to phi 1 and another with respect to phi 2. So in higher dimensional Hilbert space, so suppose if there were another phi 3, then we had to add the expectation value of M with respect to phi 3 also. So just adding the expectation values with respect to the basis states. So that is what is the meaning of taking the trace in a complete and orthonormal basis. So another important thing to notice is that this complete and orthonormal, these two adjectives are very important here, because if the basis is not orthogonal basis, then the formula for trace will be significantly different from this formula of just simply adding the two expectation values. So you just have to keep in mind. But in quantum mechanics, we usually encounter the orthonormal basis, so we don't need to worry about the more general case. So just keep in mind the special case of orthonormal basis. So this is the, so what I want to say is that this is the trace formula with respect to an orthonormal basis. So that's that. So now what we need to do is just to find these expectation values. Like you can easily compute this, what do we call this? So this is just a matrix element of the M operator. So how to calculate this? This is very easy. So M was this one. So just put this here. So now this, and now it is easy to calculate this inner products. So in the previous assignment you have already done so, and in this week's assignment also you will get to practice a lot about how to find inner product. So you need to find these two inner products and multiply them, and this will give you the numerator of this first term, and the denominator is already 1 because we are told that psi 1 and psi 2 form an orthonormal basis. So that means phi 1 and phi 2 are already normalized. So the denominators are 1 in both cases. We need to worry about only the numerators, and in the first case the numerator is given like this, and now just find the two inner products and multiply them. So how to find this inner product? Phi 1 psi. So this is very easy, like just take the inner product with phi 1 here and use the fact that phi 1 and phi 2 are mutually orthogonal. That means the inner product between phi 1 and phi 2 is 0, and you are only left with this phi 1. So inner product between phi 1 and phi 1, and that is 1 because phi 1 is normalized already. So that means this phi 1 psi inner products give you the answer 9i. Okay, and similarly this inner product, how to find it? So now this is the inner product between the bra chi and ket phi 1. So we have found this bra chi and just multiply with ket phi 1 in the right hand side of it. Again, so phi 2 and the inner product between phi 2 and phi 1 will be 0 because they are orthogonal, and the inner product between phi 1 and phi 1 will be 1, and thus you are left with I by root 2. So the answer of this inner product is I by root 2. Simple. Now multiply this 2 and you get this first matrix element as this, so minus 9 by root 2. Similarly the second term, so denominator is 1 and the numerator you do the same thing, like M was defined like this outer product, and then you have to take this to find these two inner products and again multiply them, and we proceed in the same way again, like inner product between phi2 and psi. What will be the result? Because phi2 and phi1 is orthogonal, so that is 0, and phi2 give us 1 because that is normalized, and that means our result is 2 for this first factor. So this is this 2, and for the second one, so chi phi2, this will give us 1 by root 2. So that means this second term has a contribution of 2 by root 2. And finally, to find the trace, add these two contribution up and you will get the answer. So this is our final answer. It's minus 7 by root 2. So that is how you take the trace of an operator in an orthonormal basis. So as I said, the adjective orthonormal and complete are very important because in non-orthonormal basis the trace formula is significantly different from the one we have used. So this formula for trace is valid only in orthonormal basis, and nothing to worry about because in quantum mechanics we usually encounter only orthonormal basis. So the first problem is done. So I think there is no question because it was very easy. So but still feel free to ask if you have any question, otherwise I will proceed to the second one. Okay, so I don't think there is any question. So let us now look at the second problem. So we are given a state psi. So this is the state psi, this is given, where phi1, phi2, phi3 are three orthonormal states. And but by inspection you can see, and also it is given in question, that psi is unnormalized, because if you take the so with the given coefficients, if you take the inner product of psi with itself, you will see that this will not be equal to 1. So that means psi is unnormalized, but psi is just given as a linear combination of three mutually orthogonal states, and those states are also normalized. Okay, so these three orthonormal states, psi 1, psi 2 and psi 3, so they are said to be eigenstates of an operator B. Okay, so they are eigenstate of some operator B such that, so the eigenvalue eigenvector equation is given like this. So psi n are the eigenstates of an operator B, and this is the eigenvector eigenvalue relation. So B acting on psi n gives us the eigenvalue n square plus 1. So and this is valid for all the three, phi 1, phi 2 and phi 3. That is what is written here. So we have to find the expectation value of B for the state psi. So pretty standard setup. So how to find the expectation value? So this is, we know this is the formula to find the expectation values. So the expectation value of B in the state psi is given by this formula, right? So this is the numerator and this is the denominator. So we usually do not write the denominator because most of the time the states in which we are finding the expectation values are already normalized. But here this is unnormalized, so the denominator will play a non-trivial role here. So you see the denominator will not be equal to 1 because psi is not normalized, and so this is the actual formula for finding the expectation value. So now let us find the numerator and denominator separately, and then you will get the answer. So okay, so first find the denominator. So inner product of psi with itself, and as I said in the beginning, so this will not be equal to 1, and that is why it is unnormalized. So first write the bra corresponding to this given kth state. So this is simply equal to this, and the kth is already given as this. And now use the fact that phi 1 and phi 2 and phi 3 are mutually orthonormal. So that means all the cross terms like inner product between phi 1 and phi 2, or phi 2 and phi 3, or phi 1 and phi 3, all these cross terms are 0 because they are orthonormal. And only these terms like inner product between phi 1 and phi 1, so this is 1. So similarly inner product between phi 2 and phi 2, and inner product between phi 3 and phi 3 are all 1 because they are, so phi 1 and phi 2 and phi 3 were normalized, and all the cross terms are 0 because of the orthogonality. So that is why we are left with, so you simply get, so from this first term, so inner product of this and this one, so from these two you get this half, and from this second thing you get this 1 by 5, and from the third you get this 1 by 10. Add them up and you get 4 by 5. So you see this psi, so inner product between psi and psi is not 1, so this is only 4 by 5. So our denominator is 4 by 5, and what about the numerator? So the numerator is, so to find the numerator we have to first find these states, so the operator B acting on psi, and after finding these states we have to take the inner product of this state with this bra psi. So first find this state that is produced when B is acted on kth psi. Okay, so and of course B is a linear operator, so that is not given explicitly, but in quantum mechanics we always assume that the operators with which we are working, so they are all linear operators. So that means they act separately on all the constitute kth states, right? So that construct this psi by linear combination. So B act on all the basis kth states separately and linearly. And now acting on phi 1, so this is just B acting on phi 1, the first thing. So the first component was this 1 by root 2 phi 1, and B acting on phi 1, and B acting on phi 1 is this, because B acting on phi 1 is this one. So B acting on phi 1 will give us 1 square plus 1 phi 1, so 2 phi 1. So similarly here we have 2 phi 1, and this 1 by root 2 factor, this is just the contribution to the linear combination. So similarly for the second one, so B acting on phi 2 gives us 2 square plus 1 phi 2, so that means 5 phi 2. Similarly for the third one, so B acting on phi 3 gives us 3 square plus 1 phi 3. So just do this manipulation and you will get this result. So the result is the state that is produced when B is acting on ket psi is this one. So root 2 phi 1 plus root 5 phi 2 plus root 10 phi 3. So this is the new state that is produced after the action of B. And now we need to take the inner product of these states, this highlighted state, with the ket psi. So our original psi. So take the inner product of this bra psi with this new ket that was produced after B was operated on psi. Now again use the similar orthonormality conditions and you will get 3. Because like this first term, this is action of this term is non-zero only when this is acting on this root 2 phi 1, right? Because of orthogonality condition, and phi 1 is normalized already. So phi 1 inner product is 1, and this 1 by root 2 and root 2 cancels each other and give you 1. Similarly this second term, and it acts on this, and this last term acts on this. So all of them will give you 1 and add them up to get 3. So our numerator will be 3. Now just substitute the values for this numerator and denominator and you will get the result 15 by 4. So this concludes the discussion on our second problem. So if you have any question, please ask. Otherwise I will move on to the third one. So that is a much more involved problem. No, let us do it first. Okay, so let us move on to the third one. Like this was the question, as you recognize. So it was on your study material 4, but I decided to discuss it again because this is much more involved and this mimics a physical scenario, because till now we are only doing just linear algebra mathematics with not much connection to physics, but this problem will help us to get an idea. So what is the physics of quantum mechanics, like why it is non-trivial from our usual classical mechanics setup. So the question is, a physical system has a Hamiltonian H and it is in an initial state psi naught. Okay, so we know the Hamiltonian and an initial state psi naught. They are given by this. This is the Hamiltonian and this is the initial state. This is the initial state. So you see our Hilbert space is three-dimensional because we are denoting the Hamiltonian as a 3x3 matrix and this initial state psi naught as a column vector of dimension 3. So the question is, given this Hamiltonian and this initial state, so what are the possible results of measurement of energy of the system? So this part is not important, the state psi naught. So the question should have been, so what are the possible results of measurement of energy of the system? So this is one question, and since there are there are more than one possible result, so we have to also find, so there are more than one possible results and we have to find the probability of finding each result. Okay, so there are more than one possibilities and the different possibilities come with different probabilities. So all these things we have to find, and then finally we will also find the expectation value of the energy. So this. So okay, so I hope you have looked at the study material. And so possible results of measurement of energy. So what is that? So in quantum mechanics, so those will be the eigen values of this H matrix. So possible results of measurement of energy will be the eigen values of H. So this is one result, and probability will be given by the we will see. So for now, remember that the possible results of the measurement of energy is the energy eigenvalues. Yes. So we need to find the eigenvalues of given H, and these eigenvalues are the possible results of the energy measurement. So now we have to find the eigenvalues of this given 3x3 matrix. And how to find? So let the eigenvalue be lambda E naught. So this will give you the eigenvalue equation. So determinant of this thing, so H minus lambda E naught I. So determinant of H minus lambda E naught identity matrix should be 0, right? So that is how you find the eigenvalues. So that gives us this condition. So determinant of this should be 0, and find the determinant of this 3x3 matrix, and you will get the determinant is this. And now solve this equation to find its roots, and you see the roots are lambda equal to -1, -1 and +1. So you see, so only two roots, +1 and -1, but multiplicity of the root -1 is 2. So minus 1 is a double root. Now let us first find the eigenstate corresponding to plus E naught. Okay, so since lambda is this minus 1 and plus 1, so the eigenvalue will be obviously minus E naught and plus E naught. Okay, so the possible results of energy measurement will be either minus E naught or plus E naught. So these will be the two possibilities of our energy measurement. So minus E naught or plus E naught. Okay, so that answers our first question. So possible results of energy measurement. Now find the probabilities of each result. So you see, so we have just found the eigenvalues of this Hamiltonian. Now of course there will be corresponding Hamiltonian eigenstates. Okay, and psi naught is given as some column vector. So psi naught is explicitly given as some column vector, so some state, and we will find Hamiltonian eigenstates, and we will we would like to find psi naught as linear combination of energy eigenstates. So linear combination of energy eigenstates, and the coefficients that will appear in the linear combination will be the probability amplitudes, and the mod square of those probability amplitudes will give us the probabilities of each result. So that is how we do it. Like consider this. So consider this. So psi naught. So for now just note this. So I'll explain later. So psi naught is the linear. So this is the linear combination of the energy eigengate. So this plus, this minus 2, and this minus 1. So these three are energy eigengates, and I have just expressed this given psi naught state as the linear combination of the energy eigengates. And you see these coefficients like minus I root 2 by 5, this minus and this plus 1 by root 5. So this gives us probability amplitudes. And if you take mod square, so like if you take the mod square of this thing, so that will give you 2 by 5, and that will give you the probability that you will get your energy measurement result as plus E naught. So those will give you the probability. So how to do that? So let us now discuss. Right? Okay. So till now we have just found the eigenvalues. Now we need to find the eigenvectors. So now you know how to find the eigenvectors corresponding to one eigenvalue of a square matrix. So eigenstate corresponding to plus E naught correspond to lambda equal to plus 1. So put lambda equal to plus 1 in this matrix, and that gives us this matrix, and the eigenstate corresponding to plus E naught or equivalently lambda equal to 1 is this one. So if ABC is the eigenstate, the corresponding eigenstate, so then it has to satisfy this relation. Okay, So now you have to find a column vector whose components are A, B and C that satisfy this condition. Okay, and you see, so by inspection you can see that a normalized uh, eigenstate that satisfy this just discussed relation will be this one. So this plus. So a normalized eigenstate may be this one. So 1 by root 2 I 1 0. So this is normalized. So 1 by root 2 is the normalization factor. So how to find these eigenstates? So there is no general algorithm, so you can rely upon observation, and this will be much more easier with some practice. So here you see, as a quick check, so if you put A equal to I, B equal to 1 and C equal to 0, so you will see that all of them, so you will get a 0 in the right hand side. Like, so 0 means the column vector in the right hand side will be 0, 0 and 0. That is written as 0. So that is how you find the eigenstate corresponding to plus E naught. Now, so similar thing need to be done for the minus E naught eigenstate and minus E naught. Okay, and minus E naught means what? Minus E naught means lambda equal to minus 1. So put lambda equal to minus 1 here, and that will give you this thing, this matrix. And similarly, the eigenstate corresponding to minus E naught or lambda equal to minus 1 will be such, like if it is A dash, B dash and C dash, so that corresponding eigenstate need to satisfy this highlighted relation. Okay, and now by inspection you can see that if you take A dash and B dash both 0 and C dash equal to 1, then this relation, highlighted relation, is already satisfied. So that will be one eigenstate corresponding to lambda equal to minus 1, and 0 0 1 it is already normalized. And then another one you can take like this. So 1 I 0 and this normalization factor of 1 by root 2. You see, just substitute A dash equal to 1, B dash equal to I and C dash equal to 0, and you will see this relation is satisfied. And you can also check that the two eigenstates that I have written, so they are normalized, but more importantly they are mutually orthogonal. They are mutually orthogonal. So, and in these kinds of problems we not only try to find the eigenvalues and eigenstates, but we also try to make the eigenstates mutually orthonormal, right? So I hope you are familiar with the Gram-Schmidt orthogonalization, because in previous week's tutorial problem there was one such problem. No, probably not previous week, but on some previous week's tutorial discussion there was a discussion on Gram-Schmidt orthogonalization, right? So you are given two linearly independent vectors and you have to make them mutually orthogonal. So you can use the Gram-Schmidt orthogonalization procedure to do that. So in quantum mechanics, so we usually have to use the Gram-Schmidt orthogonalization procedure in the degenerate sector, because in the degenerate sector of an Hermitian operator, so eigenstates may not be a priori mutually orthogonal. So you can just find a linear combination, sorry, a linearly independent set of eigenstates in the degenerate sector, and then you can try to make them orthogonal by using Gram-Schmidt orthogonalization. Here, by inspection, I have already chosen the eigenstates as mutually orthonormal. So I do not need to use this Gram-Schmidt orthogonalization procedure. And so this -1 and this -2, these two states are already mutually orthonormal, and you can also check that this ket plus, this ket -1 and ket -2 are three mutually orthonormal eigenstates of H. So you can just easily check the orthogonality property of these three eigenstates, and they are already normalized, so they are orthonormal. So just check that easily. Now the probability. So how to find the probability? So probability of measuring plus E naught. So the measurement problem. So in quantum mechanics, what does it mean to measure? So we saw that the Hamiltonian operator that is given has eigenvalues plus E naught and minus E naught, and you will only get these two results if you measure. So after measurement, so it is said that after measurement the wave function collapses on one of the eigenvectors of the observable. So we are already given a psi naught. So if it collapses on the eigenvector corresponding to the plus E naught eigenvalue, so that will give you the result of the measurement as plus E naught. So this is the interpretation of the measurement problem. So if your eigenvalue, if your eigenvector, if your wave function collapses on the eigenvector, then you will get the result as the eigenvalue corresponding to that eigenvector. So now, to obtain the result as plus E naught, we need to collapse our wave function on these plus states. So the plus state is the eigenstate corresponding to the plus E naught eigenvalue. So the original eigenvector, the original state that is given is psi naught. So it is needed to be collapsed on this plus ket state. Only then we will get the result as plus E naught of our energy measurement. So probability of measuring plus E naught is 10. So you see, so this one. So this is the probability amplitude. Like, so we have found three energy eigenstates, and of course, so and psi naught can be represented as a linear combination of the three energy eigenstates, right? And the coefficients of that linear combination will give us the corresponding probability. So this is the corresponding probability. So so this is the probability amplitude, like, how to say it? So you are already in a psi naught state. So what is the probability that you will so what is the probability that you will get the characteristics of plus states. So this is given by this probability amplitude, and take the mod square of that and you will get the probability. So the problem is like, so you are on psi naught state. So okay, so what is the okay, so yeah, I am not finding proper words, but like you get the idea, right? So this is like finding the components of vectors. Like we resolve vectors in three components: I, so x component, y component, and z component, and then just we then just find the what are they called, like linear coefficients of the components. So this is the same problem, but this we are doing for complex vector space. So in class 12th we used to do it for real vector space. Now we are just doing for complex vector space. So and just take the mod square and you will get the probability. So this is the probability of collapsing your earlier state into the eigenstate of plus E naught. So this is the probability. Now you have to take the inner product, of course, to calculate the numerator. So our plus state was I 1 0. So and we need to find the corresponding bra. So this will be minus I 1 0 and psi naught as given in question. Okay. And psi naught is this as given in question. Now do the inner product multiplication and you will get this result. So this is the numerator. Okay, sorry. So its square will be the mod square will be the numerator, and denominator is 1 because both these plus states and psi naught state are already normalized. So you can check that they are already normalized. So this probability, this P plus is 2 by 5. So probability of measuring plus E naught is 2 by 5. So this is the same probability of collapsing this psi naught state into the corresponding eigenstate of the eigenvalue plus E naught. So this way, this is the probability of measuring plus E naught. And then we can have only two results, plus E naught and minus E naught. So the rest will be the probability of measuring minus E naught. So the probability of measuring minus E naught is just 1 minus P plus, because total probability need to be 1. That is the what? So unitarity condition. So probability, total probability should add up to 1. So the probability of measuring minus E naught is 1 minus this P plus, and that is 3 by 5. So these are the two probabilities. So our final statement is this one. So possible results of energy measurement is plus E naught, plus E naught with probability 2 by 5, and minus E naught with probability 3 by 5. Now of course, so these are the possible results with the possible probabilities. Now of course, what are the expectation value? You can just directly find them from here. So probability 2 by 5 multiplied by the corresponding value E naught, and the probability 3 by 5 multiplied by corresponding value minus E naught, and that will give you minus E naught by 5. So that is the expectation value. So, but you need to remember that you will never get this expectation value as a result. Like in general case, you do not get the expectation value as a result of the measurement. This is just the average of all the measurements. So this is the weighted average with all these probabilities of a measurement. So upon measurement, you may only get plus E naught or minus E naught. So nothing other than that. But the average value of the measurement, like so it's like coin toss. So like what are you seeing? What we are seeing? So this is like a biased coin. So suppose plus E naught is head and minus E naught is tail. So we get plus E naught 40% of the time and minus E naught 60% of the time. So of course, so upon coin toss, you only get head or tail. So you do not get like is something in between. So this is similarly this is like that. But the expectation value like this. So another thing I just wanted to show you quickly, so how to find the time evolution. So I do not think the time evolution has been covered in the lectures, but it is pretty easy. Okay. So but it is not very difficult. So time evolution, so the problem statement is you are given so psi at time t equal to 0. So psi at time t equal to 0 is psi naught, that we are given already. So you need to, and you also know the Hamiltonian that was given in the beginning. So we need to find psi at an arbitrary time t. So the initial value of this psi is given, and we have to find psi at an arbitrary time. So how to do that? So this is the relation. So this is how you find time evolution, the highlighted one. So psi at t is given by e to the power minus I h t by h cut acting on the initial value. So acting on psi at t equal to 0. This is the time evolution relation. Now the easiest way to do it. So how to do it? So psi at t equal to 0 is given like this. So this is psi at t equal to 0, but we saw that this was not an energy eigenvalue. So this will have, so if you try to do matrix multiplication directly, then that will be very difficult to do, because psi at t equal to 0 is not an energy eigenstate. So what to do? So we usually find the resolution of this psi naught in terms of energy eigengates. So, and we saw that these three energy eigenstates are mutually orthonormal, and that means they form a complete basis. Okay, complete basis means so this relation. So this outer product. So sum of these three outer products is identity matrix. So this is the meaning of a basis being complete. So now we will represent psi naught like this. So psi naught, of course, it is equal to identity operator acting on psi naught. This is trivial. Now use the completeness relation. So in place of identity operator, I have just used the completeness condition, completeness relation, and then so we can easily find these three inner products. So we have calculated plus and psi naught, and you can easily calculate this inner product and also this inner product. Calculate this and you will see that this is the resolution of psi naught in terms of the energy eigengates. Now it is easy to act with this evolution operator. Now of course you know, so if plus is a energy eigenstate, so that means H acting on this plus give you E naught, this plus state, right? So of course, so e to the power minus I h t by h cut, so that will just give you, so that will be another eigenvalue equation. So this will then be the eigenvalue e to the power minus et by h cut, and plus psi, this is already an eigenvector of h, and of course this will remain an eigenvector of h. So this is the eigenvector relation for this evolution operator. So the eigenvector remains the same and eigenvalue changes correspondingly. So just exponentiation. So this is for this plus component. Similarly for the minus component, the eigenvectors will be the same, remain same, but eigenvalue will be e to the power minus I multiplied by minus e t by h cut, and that gives e to the power I e t by h cut. So this is your final result of time evolution of the given initial state. Okay, so this was a little involved problem. So if you have any question, please feel free to ask. Otherwise, let us move on to next one. Okay, so now this is again another assignment question of probably previous year. Okay, so show that the eigenvalues of a Hermitian operator are real. So this is one statement, and another is that we have to also show that the eigengates corresponding to different eigenvalues of a Hermitian operator are orthogonal. So let us first show that the eigenvalues of a Hermitian operator are real. So this is easy to do. So let A be a Hermitian operator, and Hermitian with this. Okay, Hermitian means this, and let alpha be a normalized eigenkette of this Hermitian operator that satisfy this eigenvector eigenvalue relation. Okay, so please don't be confused with this notation. So alpha is, so the alpha that is written outside of this kate is a number, and this alpha that is written inside this kate, so this kate alpha is the state. So I have just written it like this. So okay. Now to do, now let us, okay, so we have to check whether the eigenvalues of the Hermitian operator are real. So we need to extract the eigenvalue alpha from this relation, and we have assumed that this alpha kate is a normalized eigenkette. That means we see that if we can somehow act with this alpha bra in the right hand side, then due to the normalized condition, the right hand side will give you alpha. So that means we have to act with alpha bra in both left hand side and right hand side, and that is what I do here. So I have acted with both alpha bra in LHS and RHS, and the result in the RHS is simply alpha, because this kate alpha, so the alpha state is normalized. So okay, that much is fine. But now let us take the complex conjugation of that thing. So take the complex conjugation of this thing, but this also means that the expectation value of alpha of A dagger in the state alpha. So that is the definition of Hermitian adjoint thing. But we are, but in the question it is given that A and this operator A is Hermitian. So that means A dagger is equal to A, and that means our result is again alpha. But also directly we can see that if you just directly take the complex conjugation, and in this result, in this step our result was this expectation value of A was alpha, and just you can also just take the complex conjugation directly and the result will be alpha star. But we have also shown that the complex conjugation also lead to, so upon these three steps the result is also alpha. So that means alpha star equal to alpha, and that means the eigenvalue alpha is real, and that is valid for all eigenvalues, because there was nothing special about alpha. It was just an eigenvalue of this Hermitian operator. So that means all the eigenvalues of a Hermitian operator are real. Okay. So now using this fact, we will now show that the eigenkettes corresponding to different eigenvalues will be orthogonal. Eigenstates corresponding to different eigenvalues will be orthogonal. So let us now take two eigenstates with different eigenvalues. So consider this. So one eigenstate is alpha 1 and another is this. So the eigenvalue is alpha 2 and alpha 1 is not equal to alpha 2. Okay. Now uh, let us act with bra alpha 1 on both hand side of this relation. So that is what I have done here. I have acted with bra alpha 1 on both hand side. Okay. So this gives us this relation, and now take complex conjugation on both hand side. That means you will get this relation, but as we see, complex conjugation in the left hand side will give us this one. So alpha 2 in the leftmost, then A operator, then alpha 1. So here it should have been A dagger, but since A is Hermitian, so A dagger is A, and that is why I have just written A. Okay, so this was the left hand side, and in the right hand side we have just shown that alpha 2, so that is the eigenvalue of A, must be real. That means alpha 2 star will be alpha 2, and we know that this complex conjugation relation of inner products, so alpha 1 alpha 2 complex conjugation is equal to this alpha 2 alpha 1. So the bra and ket will be interchanged. So this is the relation. So one of our relation is this one. Okay, and so this looks familiar because we can also act with alpha 2 bra on both hand side of this relation. Now we'll do that here. So now we have done it here also, but so while the left hand sides are same, we see the right hand sides are not same right now, so they must be equal to each other. So equate those two and you will get this relation, and we have chosen alpha 1 and alpha 2 such that they are not equal. That means the only thing to satisfy this equation must be this. So alpha 2 and alpha 1 should, so this inner product between bra alpha 2 and ket alpha 1 should be 0, and that means this alpha 2 and alpha 1 states are mutually orthogonal. And since there was nothing special about alpha 1 and alpha 2, and this conclusion is valid for all the eigenkets provided that they are non-degenerate, because in this proof we have chosen that alpha 1 is not equal to alpha 2. So that means nothing else is needed. So as long as alpha 1, so as long as the eigenvalues are different, so the corresponding eigen vectors of a Hermitian operator will be mutually orthogonal. So that is the statement. Now there is a subtlety for degenerate sector. Now for the case of degenerate eigenvalue, you see we have taken in this proof we have taken alpha 1 not equal to alpha 2. But look at this degenerate case. So let alpha, state alpha and state alpha dash be degenerate. That means they both correspond to eigenvalue alpha, but the states are different, like they are not connected with a phase multiplication, but they are different. So if you just follow the above procedure, so in this step, so if you follow the above procedure in this step, you will see that here you have alpha, and here you will have alpha also, and both left hand side and right hand side will be exactly equal to each other, and you will not be able to conclude anything. So in the degenerate sector, the above argument cannot conclude the orthogonality between alpha and alpha dash. At most, what we can do, we can only take them to be linearly independent. And then, after choosing to linearly independent, some linearly independent alpha and alpha dash, we can use the Gram-Schmidt orthogonalization scheme to make the degenerate eigenkets mutually orthogonal. So that is where this Gram-Schmidt orthogonalization procedure will play a significant role. So you choose linearly independent eigenvectors, and then you use the Gram-Schmidt orthogonalization procedure to make them orthogonal. So that is that. And now the final problem of this session. So this is the uncertainty relation. So we know the Heisenberg uncertainty relation for momentum and position, but uncertainty relation is much more general than that, and the statement is this. So let A and B be two observables. So you know observable means Hermitian operator, and when you say Hermitian operator, so all of the special properties of such operators come into mind. So A and B are two observables, that means they are Hermitian operators. So prove that for any state, so you see there are several expectation values. So for any state means, so take this expectation value over any state. So prove that for any state this relation holds. So this is the generalization of Heisenberg uncertainty relation. So this means, so root over of these things, so this means this. So you remember we used to do this delta x, delta p for infinite Hall potential or simple harmonic oscillator. So this is the, what do you say? So this is the standard deviation. So this is the error in measurement of the position. Uncertainty in the measurement of A. So this is that thing. So this is the uncertainty in the measurement of A. So this whole thing. And similarly, this is the uncertainty in measurement of B. And this is the modulus of the expectation value of the commutator of A and B. So you know the uncertainty. So the uncertainty in measurement of A is given by this relation, right? We all know this. So this is the expectation value of A square minus square of the expectation value. So this is the square of the uncertainty. Now we can define an operator. So here please note that, so here in the question, so this is just a number. Okay, so this is just a number, but I mean more importantly this delta square, so this is just a standard deviation, just a number. But now I am defining an operator, so delta A hat. So hat means, so I am defining an operator. like this. So A minus expectation value of that operator. Of course, this is a state dependent statement, but still, since this is what we will show will be valid for any state, so this proof goes through. So let us define an operator. And you see, if A is Hermitian, so this delta A operator will also be Hermitian, because this is just a number. So this is actually expectation value multiplied by identity operator. So this is just a number. So this is of course Hermitian, and A is also Hermitian. So that means delta A is a Hermitian operator. Now, if you take the expectation value of the square of this delta A operator, so and see and expand this. So let us expand this. So this is just the expansion A minus B whole square formula. And now take the expectation value. So this first term gives us this expectation of square. Now the third term goes through. This is just a number, so there is nothing to have an expectation value, and this number will just come out. But this term, you see, this will give -2 of this thing, and that is why we get this overall minus sign. So you see, this part is just a number, so just you can treat it as a coefficient, like a constant coefficient, and this is not an operator. But this part is operator, so I hope it is very easy to convince yourself that this will be the result. Okay, so similarly, so what we have shown is that the expectation value of the square of the delta A operator that we have just defined is equal to the square of the uncertainty in the measurement of A. Okay. Now you can of course do the similar thing for B also. Similarly define a delta B operator. Okay. And now define a total thing like this C operator. So define another C operator where lambda is a real number and this is I lambda. So lambda is a real number, and of course we know that the expectation value of C dagger C is greater than equal to 0, right? Because C dagger C is a what we call, so it is a Hermitian operator, and we know the expectation value of Hermitian operator. Well, no, that is real, but okay, so C dagger C, the expectation value of C dagger C is greater than equal to 0, so it is like a square of a state. So it is like a squared norm of a state. So I think this was discussed in the study material for this week, that this C dagger C should be greater than 0. Expectation value of this one should be greater than 0, and please look at that, and I've just used this information. So since C dagger C expectation value is greater than 0, now we have just used this explicit formula for C. So this is C. Of course, now take this dagger and you will get this. So C dagger will be this one. So because delta A was Hermitian, delta B was Hermitian, lambda is real and I equals to minus I. So this is the C dagger thing and this is C. Just now multiply them, and while multiplication you need to be careful of the order of the operators because operators in general do not commute. So you will get 4 terms when you multiply these two things. So one will be delta A whole square, another will be lambda square delta B whole square, and another will be this. So I lambda delta A delta B minus delta B delta A. Just look carefully and you'll understand. So this much is fine. Now you see the commutator of delta A delta B is equal to the commutator of A and B, because as you see this is A minus a scalar, so A minus a number and commutator of an operator with a number is 0, so they always commute. So only the non-trivial commutator will be between A and B, and so commutator of delta A delta B is equal to commutator of AB. Now we get this. So to this much it is fine. Now we know that, so this looks like a quadratic equation in lambda, but there is one coefficient that looks complex, but we will now show that that is not the case. So this is a purely real quadratic inequality. So we want to show that. So for that, let us note that, so if A and B are Hermitian operators, so in previous week we saw that the commutator of A and B will be an anti-Hermitian operator, right? And since A and B is an anti-Hermitian operator, that means it can be written like this: AB commutator is equal to I-O operator, where this O will be a Hermitian operator. So AB can be written like, since AB is an anti-Hermitian operator, it can be written like I-O operator, where O operator is Hermitian operator. Thus we see this expectation value. So expectation value of this AB commutator multiplied by I will be equal to, of course, minus of the expectation value of O, right? And O is a Hermitian operator, and we know that the expectation value of a Hermitian operator is real. So I think this was also discussed, and if this is not discussed, you can just follow the argument that we followed, so that we presented in question number 4. So by similar argument, you can also show that the expectation value of a Hermitian operator over any state is a real quantity. So that means this total quantity is real. Okay. And now the quadratic inequality looks like this. So of course this will be so this is of course a real quantity, because this gives a standard deviation or uncertainty thing, and the second thing also, lambda square is real and this coefficient is also real, and in the third term also we have just shown that this expectation value of a Hermitian operator will be real quantity and lambda is real. So So now that much is fine. So this equation inequality 1 is a real quadratic inequality. So all the variable lambda and the coefficients, the three coefficients, all of them are real quantities. Now we can also show that this expectation value of this delta square operator, so this is a positive thing, because of course so we showed that this delta is a Hermitian operator. So that means delta A is equal to delta A dagger. So out of 2 delta A, I have written one as delta A dagger and I have kept another as delta A. But we know that for any operator this relation holds. So C dagger C greater than equal to 0. So this relation, so for any operator O, or suppose for any operator M, so the expectation value of M dagger M will be 0 or positive. So that follows from our positive norm assumption. So for any operator M dagger M is greater than equal to 0. So that means this coefficient is positive and the coefficient of lambda square, this is also positive. Okay. So now we will use the property of quadratic equation. So that we usually learn in class 11. Now, so we have the quadratic equation, a quadratic inequality 1, and the coefficient of the quadratic term is positive and coefficient of the constant term, and the constant term is also positive. So that means this inequality 1 will hold only if the discriminant is less than equal to 0. So when this happens, so this will happen only when the discriminant will be less than 0. So there are other conditions, but we do not need to worry about them because we have shown that the coefficient of the quadratic term is positive and the constant term is also positive. So those are automatically satisfied. Now the only thing we need is to demand that the discriminant has to be less than equal to 0 if this inequality 1 is to hold, and the discriminant will be this one. So square of this term minus 4ab. So if it is a lambda square minus b lambda plus c, so a lambda square minus b lambda plus c, then the discriminant is b square minus 4ac. So just compare and you will see this is the discriminant, and for inequality 1 to hold, this has to be less than equal to 0, and from there you get the generalized uncertainty relation. Now, okay, so this thing is the square of the uncertainty in the measurement of A. So now just take square root in both hand side and we'll find this one, and in the final step just write it like this. So this is the mod. So this is the relation. This is the generalized uncertainty relation. So okay, so this was somewhat involved proof. There are other ways to do also, but this is the most direct route. So that concludes today's session. So if you have any question, please ask. Otherwise, we will meet next week. Okay, so I think there are no more questions. So let us end it here. Okay, bye. See you next week.